start recording, and when I go around, start the recording from this camera. Okay, so like I was saying, you don't need the little high-res camera, not super high-res, but some. It only has 8 gigabytes on the memory card of 8 gigabytes, so it only saves for 70 minutes. It only records for 70 minutes. But maybe we can, if somebody reminds me, maybe we can take a break in the middle. Because there is, like, what day is it today? Today is Wednesday. Like Monday. Monday was quite a heavy day. Today is also a heavy day. So we're going to talk about minimum spanning trees. And that's a very standard thing. Oh, wait. Yes, good. It is recording. Everything is recording. So minimum spanning trees are a standard topic in pretty much all third-year algorithms courses. But we're going to add a little bit on. Most people frequently cover only Kruskal's algorithm. We're going to cover Kruskal's algorithms, the proof of correctness, obviously, Prim's algorithm, the proof of correctness, and then we're going to talk about why you would want to use one or the other. And in particular, we're going to talk about the implementation of Kruskal's algorithm, which is, it sounds really easy until you ask a question, okay, how would you do that? And then you think, okay, that requires a sneaky new data structure, which one of the learning objectives of this course is learning how to use sneaky data structures in the design of your algorithms. So this is good. But maybe we can take a break if people remind me, and we have time between the proof of correctness and Prim's algorithm and the implementations. By the way, if people are shy and don't want to, I don't know if you can put up your hand or ask a question anonymously in this, but if you want to, you have my WhatsApp number. So if I set this so it will make noise, then you should be able to, yeah, it says it's, you should be able to WhatsApp me. Somebody has a question?
Yeah,
Sure.
Travis, they can also send me private message in the chat,
Oh.
so I can also let you know if they have questions, if that works better.
Perfect. Great. Yes, this works too. Okay, so so Sarah is here to be the moderator and keep things running properly. Okay, so minimum spanning trees. So like most of the classes recently, you start off, you're given a graph. You're given a graph, say this graph, and it's the edges have weights, so edge-weighted graph. And the idea is you want to, now it's a connected graph. We assume it's a connected graph, otherwise this is impossible. Connected means you can get from anywhere to anywhere. And you want to find a tree which spans the graph, which means the tree includes every vertex in the original graph. So that's spanning. It's a spanning tree, and you want it to be minimum, which means that the total edge cost of the edges in the tree is minimized. Okay, so you can think about this like you have towns and you have roads, and you want to pave the roads such that it's possible to get from any town to any other town driving only on paved roads. Okay, or you have electrical devices, you want to put cables such that the current, like, you know, Christmas lights, like you have to connect all of them such that you can, all of the electrical devices get power from some source, or you have some electrical networks or networks of like fiber optic cables or whatever. Okay, so you don't care in this problem. You don't care what is the width of the graph, the time it takes you to get from any town to any other town. You just care that they're connected, that you can get from one town to any other town, driving possibly a really long way, but on paved roads. And you want the total cost to be minimized. Okay? Everybody get this? Good. So this is an instance. You have towns which are conveniently labeled from A to I. I drew this, so this is in the textbook. I drew this last night, at least it's in my edition of the textbook from the 90s. How do you do this? So how do you do this in polynomial time? Well, you do this with a greedy algorithm. Well, so there are actually, we're going to see two algorithms. There are a lot of algorithms. People have solved, this problem has come up over and over again throughout in history, and people have solved it many, many times. Okay, this is not like Karasuba's algorithm where people multiplied the slow way until 1962 and finally there was a breakthrough. People ran into this problem and solved it a variety of ways. So I think on an exam in the fall, I taught Prim's algorithm, Kruskal's algorithm, Prim's algorithm, and then I gave, on an exam or an assignment, I gave Brugge's algorithm. Okay. So, Kruskal's algorithm. So, what is Kruskal's algorithm? Well, Kruskal's algorithm is sort of it's a greedy algorithm. So we sort things. Remember, greedy algorithms, you tend to sort things and then you take things, and if you can take them, you take them in the sorted order. Sometimes after taking stuff, you resort. We'll see that with Prim's algorithm. Kruskal's algorithm, you sort things, you take them, if you can, you take them, and if you can't, you throw them away forever. Okay. Now, in some super sophisticated greedy algorithms, you take them, you throw them away. Maybe you can revoke things. You take it, and then maybe later you throw it away. In this case, we don't get into that in this course, I think. So, the things we're taking or throwing away are edges. How are we going to sort the edges? How would you sort the edges greedily? What is the obvious? Max value. Okay, so we're not trying to maximize the value here. Though that would actually, yes, smallest to largest. So we're going to do it by weight, and we're going to do it by smallest weight to largest weight. So let's say the smallest weight is GH, which has weight 1, and then for G, notice it doesn't matter what order I write because this is undirected. And then I with weight 2, and this is a pain because in the actual class I made people yell things at me. And then it's CF with weight 4. There is nothing with weight 3, and AB. So we don't care about ties. So AB, CF, it's both 4. There's no 5, so is it then GI with weight 6? Anybody correcting me? No? GI, there's only one 6. CD, that's weight 7. AH, that's weight 8. BC, that's weight 8. DE has weight 9. EF has weight 10. BH has weight 11. And is that everything? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Foop. What have I missed? Oh, 14. DF HI, where's HI? HI was 7. Oh, yeah, okay, sorry. And DF is 14. Thanks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Good. Okay. So we want to take things in this order as long as we can. We can take things as long as they do not wreck our treeness. Okay. So in the we don't keep a tree. In general, we keep a forest, and then we add edges which connect trees in that forest. And so actually, we don't have treeness. We have forestness. Okay. But then when we connect all the trees in the forest, we get one big tree. A forest of one tree, one big tree. Okay. So GH. We can take it, right? Because it doesn't wreck our forestness. Okay, so originally, oh, I shouldn't do this, but because I have to, originally we have a forest which consists of lots of trees, each which only have one node, okay? So now we connect these two trees. So now there are loads of trees which consist of only one node, and one tree which consists of two nodes. Okay. FG. If we take FG, does it wreck our forestness? No. Okay. We can take it. So we take it, we take it. CI. Does it wreck our forestness? No.
Travis, I think
Yep.
the marker is not very clear to see from our perspective. It's not very obvious.
Okay. Is that better?
Yeah.
Okay. CI. We take it. CF. This should be better on the high-res camera. CF. We can take CF. It doesn't wreck our treeness. AB doesn't wreck treeness. GI. Where's GI? Okay, does GI wreck our treeness, our forestness? If I take GI, do I have a forest? Yes, because this creates a cycle. A forest is an acyclic graph. It doesn't contain cycles. So I cannot take GI. Can I take HI? No, because it also creates a cycle, right? So I cannot take HI. CD. Where is CD? CD. Can I take CD? Yes. AH. Can I take AH? Who says yes? Okay. Yes, we can take AH. BC. BC, can we take BC? No, because that would create a cycle, quite a long cycle, right? So we cannot take BC. DE. Where is DE? DE. We can take it. Oh, so there are some cool things to know about trees. A tree on n vertices has n-1 edges. You can use that in one of the questions on a homework assignment because given a graph, you can figure out given a graph, you can figure out how many edges you have to delete to leave a tree. That comes up in question something. Okay, EF. EF, can we take it? No. This used to, in a class, I could like point to people and say, EF, can we take it? Stop looking at your phone. Tell me about EF. I can't do that so easily now. Okay, BH. BH. So actually, using that thing I just said about the number of edges, you can actually tell that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8. So actually, we can't take any of these. But we can look at BH. Where is BH? BH. We cannot take it. It creates a triangle, which is a cycle. DF. DF, we cannot take it because it creates another triangle, which is a cycle. So, that's Kruskal's algorithm. That's pretty easy, right? Anybody have any questions about Kruskal's algorithm? There's one question you could ask, which I will defer to the second half of the lecture. But if not, we can keep going. Okay? So, that problem definition. We've done the problem definition. We have done Kruskal's algorithm. Now we want to do the proof of correctness. Well, we've been talking about how to do proof of correctness.
Travis, Drew asked about this.
Is it guaranteed to make a minimum spanning tree? Yes, that's what we're just about to prove, the proof of correctness. That it does actually do what we want it to do. So yes, it is guaranteed. Okay. So how do we do one of these proofs? Well, the same way we've been doing these. I'm just going to check nobody's WhatsApping me. Oh. So how do you do a proof of correctness for a greedy algorithm according to the template we've been following? Well, you say, before we take any steps, our empty subsolution, okay. Before we take any steps, can you read this? Apparently, yes. Sarah, can you read this? Yes. Our empty subsolution can be extended to an optimal solution. Assume that after I steps, our subsolution can be extended to an optimal solution S. So when I taught this in Chile a couple of years ago, I went over this so many times. I would make them say along with me, after I assume that after I steps, our subsolution could be extended. And you know, I would get this chorus going. And then when it got to the exam, none of them wrote that. Like nothing. Why? Why did you think I was just doing that for fun? No. Okay, so we claim that after I plus one steps, our subsolution can be extended to an optimal solution S prime. Okay, so this gets into the tricky bit. Oh, yes, barely. How? I need a third whiteboard, or I need a webcam. still no webcam. But
Trevor,
in the,
would you like me to write it from the whiteboard on my end? So so
oh,
then people can see it from the shared whiteboard, but it just in that case you would not be able to see your writing on the board unless
uh, I should get a high-res webcam. It's actually, I will write, so the stuff I'm saying, this is you have seen before. When I get into the actual argument, I will write bigger. And okay, and the other thing is the high-res webcam. Apparently, this your Bright's Zoom apparently lowers the resolution depending on bandwidth. I don't know if Brightspace is that smart. But there is a high resolution recording that I will post afterwards on YouTube. Yeah, okay, I will try to write a little bit bigger. This stuff you've seen before. It's the same after I assume that after I steps, our sub-solution would be extended to an optimal solution. Eventually, you're going to know this by heart. What does that mean in this case? It means that we have considered some number of edges. Some we have taken, and some we have thrown away. And it means that there is a sub-solution which contains the edges we have. Sorry, there is an. I can just barely read it, but it's not easy. Take some decoding in one car. Sorry. I can't really move the laptop closer because then the camera is sitting on the ironing board right behind the laptop. And if I move it closer, it doesn't take in the whole board, and then people complain. I will write bigger when I get into the tricky bit. So the idea is we've taken some and we've thrown some away, and there's an optimal solution which extends what we've done. That means it comes in and it adds to what we've taken, and it doesn't take any of the stuff we've thrown away. Right. So remember this: like at some point we're waiting for the algorithm expert to arrive. They're stuck in traffic. And we've had to make some choice. You know, edges are arriving, and we're saying, yes, take this one. No, don't take that one. And then at some point we say, okay, at 12:30, the algorithm expert will arrive and say, oh, well, I wouldn't have done it that way, but don't worry, I can keep going, and we still get an optimal solution. So we assume that at 12:30. We still have this property. Oh no, like did one of those just burn out? Oh no. I think there are usually 2 light bulbs in those. Oh well. So otherwise it's still pretty bright, I guess. So at 12:30, we want to show that if we take another step, the algorithm expert can still arrive and save the day. So this is going to use one of these exchange arguments. So how the idea is, well, the easy case is for the I plus first step, we either take an edge or we throw an edge away. Okay, people are leaving. Why? Oh well. Okay, so if the algorithm expert arrives and would do the same thing, why are so many people leaving? Oh well, okay, they will watch the recording afterwards. The algorithm expert arrives. If they will take if S agrees on our first step, then we're fine, right? Okay. Suppose that S extends our sub-solution after I steps, but it doesn't do the same thing we would do on the I plus first step. For example, it could be that, what's a nice example? Here, there are ties. It's possible to take, so I think in this graph, it's possible to reorder things so that you, if you consider this, maybe it's not. Okay, maybe this graph, it's not possible to take, yeah. Okay, so in this graph, this is annoying. Why did they do it this way? It's not possible to take any, to break ties and have it make a difference to the eventual graph. I thought it was. I must have done a graph like that in the fall semester and designed it myself. Anyway, so suppose that for the I plus first step, we do something and we assume S doesn't do what we do. So there are two cases. We can, for the I plus first step, either we take an edge or we throw an edge away. When we throw an edge away, how do we know that the algorithm expert couldn't do something different on the I plus first step? I can ask somebody, some randomly selected person. If somebody would like to volunteer, okay, I will move and then scroll and scroll and scroll and scroll. Liam Hebert, how do we know that if the algorithm, if there is an optimal solution S, are you there? Liam? Okay, attempt 2. Oh, okay, you're there. You can turn your mic on. Do you have a mic? Or you can type. That's still fine. Okay, that's Okay. Okay, I can just sort of try to do this in yes and no or no questions. How do we know on the I plus first? So we're going to do the I plus first step. S. There is this optimal solution S, which on the edges, on all the edges we've considered so far, if we take them, it takes them. If we throw them away, it throws them away. How do we know that if the I plus first edge we consider, if we throw it away, we want to be sure that S must not include that edge? Well, why would we throw it away? We're greedy. We're taking the edges as much as we can. Presented with an edge, if we can take it, we take it. So when would we throw it away? It would have to break our forestness. Yes. Okay. Okay. I should have more patience. Yes. If it breaks the treeness, if it creates a cycle. If it creates a cycle with the edges that we've taken so far, we assume that S contains all of the edges we've taken so far. So it also creates a cycle in S. So S is an optimal solution. It's a minimal spanning tree. So it's a tree. It can't contain cycles. So if we throw an edge away, S must throw the edge away as well. Okay? So that leaves the tricky case. What if good. What if we consider the I plus first edge and we take it? And S says, no, I don't like that edge. I want to throw that edge away. Now, this is a bit tricky, so I'm not going to make this a question. So then S doesn't take the edge. So we consider, so let's suppose that we have S. No, don't turn yourself off. Why did it just beep? Why doesn't it? I hope it's been recording this. Otherwise, we have to rely on the Brightspace recording. And I hope the Brightspace recording is downloadable. Otherwise we don't have this. Well, we can still watch it on Brightspace, but that's kind of... So, let's suppose that we've taken some edges so far. These are the edges we've taken. So this is our forest at the moment. And S extends our forest after I steps. Right? Actually, that's a bit too path-like. Let's make it more of an interesting tree. Okay. So this is a tree. It doesn't contain cycles. So the red lines are what we've taken so far, and the black lines are what S also takes to extend our solution into a tree. So we consider some edge, and we take it, and S doesn't. So remember what I said about a tree on n vertices contains n minus 1 edges. So if we take the edge, the I plus first edge we consider, and we add it to to S, so let's suppose this is the I plus first edge we consider. You can see that this is blue and these ones are black, right? No. Okay. Better? Green? Okay. No. No, you can't see the green. The difference between green and black is not visible. Can you see the green line at all?
No, I couldn't.
Okay. So can I get bigger? So we have, so far, we have taken some edges, and S extends this by taking some more edges. Okay, now can you, the red lines, the black lines. Okay, so now maybe what we would take, this is S, and the red lines are what we've taken. And we take the next edge we see, maybe it's this one. And S doesn't take that. So S doesn't take that. So, but S has a spanning tree, a minimum spanning tree. And so if we take the edge that we would take in the I plus first edge in our order, and we insert it into S, then it's not a tree anymore, because now it has n vertices and n edges. So what that means is our our edge creates a cycle in S. Okay? So, but the thing is, so consider just this cycle. So some of the edges on that cycle may be things we've already taken, but our solution, our sub-solution doesn't contain a cycle, right? Because we can take the I plus first edge, and we take it because it doesn't create a cycle. So that means there is some edge on this cycle that we didn't take. There is some edge that S takes that we have not taken so far. In this case, this one, this black one. So if we take that edge and we remove it, the graph remains connected. Why? Because we can get from this end, if we didn't have the green edge, then we need that edge to get from here to here or here to here or wherever. But if we put in the green edge, we can still get from this endpoint to this endpoint by going around and over the green edge, right? So if you have a cycle and you take an edge out of it, you're not disconnecting anything. So that means we can take S's solution, add our edge. It creates a cycle. Find some edge in that cycle that S has that our sub-solution doesn't have, take it out, and get a tree again. Now, what can we say about this edge versus this edge? In particular, what can we say about the cost of this edge versus the cost of this edge? Anybody? Can this edge be cheaper than this edge? Have the same weight? Yes, because if this edge were cheaper than this edge, we would have considered this edge first, and we would have taken it. It's heavier or it's not lighter. It's not more expensive. So yeah. So if we take S, we add the edge we took in I plus first step. It creates a cycle. We find an edge on that cycle. There has to be one that is in S but is not in our sub-solution so far. And then we take it out. The total weight of the total cost of the tree does not go up. Okay? So that means that on the this now, what do we call this graph? Where we took S and we put in what we take on the I plus first step, and we take and we throw something away. That's an exchange. It's an exchange argument. What do we call this graph? Anybody? Yes, S prime. This is our S prime. We claim that after I plus first steps, our sub-solution can be extended to an optimal solution S prime. So if S agrees with us on the I plus first step, great, it can be extended to an optimal solution, which is S prime, which is S. S cannot take we cannot throw something away on the I plus first step, and S takes it because we only throw things away if they create a cycle with the stuff we already have. S has everything we already have, so we create a cycle in S. So the only way there can be a difference is if we take something and S doesn't, but in that case we can take S and do this exchange and we get another optimal solution S prime, which extends now everything we took even up to the end of the I plus first step. Okay? So that answers the question from a few minutes ago. Does this always give us a minimum spanning? And the answer is yes, because by induction on I, when we start, we haven't made any mistakes. And if after I steps, we haven't made any mistakes, on the I plus first step, we don't make a mistake. Therefore, we don't make a mistake ever. Okay, we end up with a minimum spanning tree. Okay. Good. How much time do I have left? Any questions so far? No. So now so that's the proof of correctness. Kruskal's algorithm, proof of correctness. Graham's algorithm. Prim's algorithm is a bit different. So let's do the same graph. Maybe it would be faster for me to rewrite this. Okay, so now remember in Kruskal's algorithm, we sort of started out considering that everything is a little tree by itself. Prim's algorithm, we don't do that. This is a G. Okay, can you still read this? Could you read this in the beginning? Maybe. Okay, so Prim's algorithm, remember we were talking about paving roads. In Kruskal's algorithm, in order to sort of pave the roads that way, to take the edges in the order of Kruskal's algorithm, you sort of need to have road building workers at every town. Well, suppose that now you have like a, I don't know, bulldozer, something you can use to pave roads, road paving machine, and you have it only at one town, right? You're trying to save money. You've only rented or bought one road paving machine, and you have it somewhere. So now you can only, and your road paving machine is you bought the cheap road paving machine, so it can't go over unpaved roads. Okay, so you can only add paved. You can drive your road paving machine around paved roads, but you can only pave roads that are incident to towns that you can reach by paved roads. Okay, so this is weak motivation for Prim's algorithm. Where do we want our road paving machine to be located initially? What's a good starting point? Which town? Between A and I. Anyone? Random choice. Yeah, anywhere. Doesn't matter. Has to work from anywhere. Where do you want it to be? F or H? Okay. F said first. Okay, let's put it at F. So F, where is F? So what Prim's algorithm does, it starts with a tree consisting of one node, which is here, which is F. And then it looks at all of the edges incident to its tree, and it adds the cheapest one. So it adds, here it adds 2, okay? And now it looks at all the edges incident to this, and it says, okay, so I can take 1 or 6 or 4 or 14 or 10. What's the cheapest edge that I can reach? So now my tree includes G. What's the cheapest edge I can reach on any of these? H. So now that adds candidates 8, 11, 7. What's the cheapest edge I can add incident to this tree? Yes. Really? What about this one? C. Yes, sorry, that's a 4. Okay, C. Yes, sorry, that's a 4. Now, cheapest edge. Okay, so this is hard to read. So it's the cheapest edge is a 2. And then here, oh, sorry, I should have said it takes the cheapest edge as long as it doesn't create a cycle. Find minimum weight edge and transfer it to the tree. Yes. That's how it works. From Wiki. Okay. Right. Okay. So far I agree with Wiki. Okay. So what's the cheapest edge? Cheapest edge 10, 14, 7, 8, 8, 7, 11. So it's a 7. I think. And then it's, well, actually, this is where we can get a difference, because it could be 8 or 8. Right, so this is going to make a difference, because if we take this one, then we'll take this edge, and we won't take this one. If we take this one, then we take this edge. Which do we like, HC or BC or AH? Vote. Okay, not voting. BC, okay, BC has it. BC, we take this one. So now our tree is like this. Now the cheapest edge is this. And now the cheapest edge we can take is this one. Okay, so this has a nice property that it's always a tree, right? So in Kruskal's algorithm, it's a forest, but this is always a tree. Why is the proof of, so that's Prim's algorithm. Please remember Prim's algorithm. It's legitimate material for quizzes, exams, whatever, except if I ask you, you don't have to memorize it because you'll have take-home exams. It's apparently on Wikipedia. So I have to come up with harder questions. So no, I wasn't going to ask you just for Prim's algorithm anyway. The proof of correctness for this is a little bit trickier. So I should go a little bit faster. Maybe we don't get a break in the middle. So the proof of correctness here starts the same way. I mean, before we take any steps, our empty subsolution will be extended to an optimal solution. Yes, that's true here. Assume that after I steps, our subsolution can be extended to an optimal solution as, yes, still the same. And we claim that after I plus 1 steps, our subsolution can be extended to an optimal solution as prime. Yes, we also say that, but the exchange argument is different. And it's not so easy. So now with Prim's algorithm, we always have a tree. And then suppose that after I steps, S extends our solution so far to a minimum spanning tree like this. Okay. So again, if on the I plus first step, we consider an edge and, well, we don't really, yeah, we can consider edges. We also consider edges and throw things away. I was skipping over that a bit. We consider an edge. If we throw it away, then S cannot, so if S agrees with us on the I plus first step, then fine, S can be our S prime. If S disagrees with us, it could be that we throw something away and S doesn't. But that can't happen because if we throw something away, then S cannot take it because we only throw it away because it creates a cycle. So that's why, I mean, we're considering things in order. Okay, I have to, it's on Wikipedia. You can read about it there. But I want to get to the implementations. These are cool. So what can be different? Well, we take something and S says, no, I don't. For example, we take BC and S says, oh, I don't like BC. S contains AH. So S would look like, instead of having A, B, B, C, it would have like this, right? And then the rest could be this. So how do we argue that if we take something and S says, no, I wouldn't take that edge, I would take this other edge. We want to argue that we can still take S's solution and change it into an S prime that extends our solution. So for example, if we take, well, suppose we take, on the I plus first step, we take this edge. Can you see this? Okay. Can you see that? Good. Okay. So this gets a little bit trickier than Kruskal's algorithm. Again, we have the solution S. We say the only way S can differ from us on the I plus first step is if we take the I plus first edge we consider and S doesn't. So let's say we take that edge and we add it to S. This will create a cycle. Okay? So now, it's this cycle. It will create a cycle. But now, the thing is, there could, for Kruskal's algorithm, we could say that any edge on that cycle, which we haven't taken so far, so in Kruskal's algorithm, any of the black edges had to be heavier or not lighter than the green edge. But now that doesn't have to be true because, for example, here when if S takes this edge and we take this edge, it's not true that this edge A, B, this is 4 and we took 8. It's not true that all of the black edges on this cycle are heavier than the edge we just took, because there could this edge, we weren't considering this edge. This edge could be lighter than this one. We couldn't consider it yet because we couldn't reach it. We're only considering the edges that are incident to the tree T we've built, to the tree we've built so far. Okay, but now I think I asked this on a quiz in the fall semester, which was very cruel. But we can say there has to be some black edge on the cycle that is cheaper or not, sorry, not cheaper, that is not cheaper, that is at least as costly, at least as heavy as the edge we take. Why? Because the cycle includes stuff that's not in our tree so far. So it leaves the tree, so the red tree, it has to leave the tree, and it's a cycle, so it has to return to the tree. Okay? And that edge, so it has to have an edge, this green edge we take that leaves the tree, and the cycle has to have another edge that comes back. Why? Because this end is in the tree, and we have to be able to go from this end and cross this edge and go around and get back here again. So it has to have some edge, like this one, that is not in the the tree and connects to the tree, is incident to the tree. So in this case, if we took this edge, if S included this edge, so we haven't taken this part, this edge before, then the if we add this to S, it creates this cycle. Okay, this is a bit fuzzy, but so in that case, we would have and our green edge is here. Okay, so this would also be black. Doesn't actually matter. This would be black. All of this more expensive stuff would be black. Okay, like black, and then this would be black, and this would be black. Can you see this? Yes, okay. So now if we add this green edge, it creates this cycle, but there has to be, so this green edge leaves the red tree, but the cycle has to come back into the red tree, and so this black edge, it has to have a black edge that is incident to the tree. This black edge cannot be cheaper than the green edge. Why? Because it is incident to our tree so far. So we do consider it, and we don't consider, so it is in our, the things we can consider at the I plus first step, that edge is in there, and we don't consider it next. We take the green edge. So that means that it can't be that this edge is cheaper. Otherwise, we would have taken this edge. So therefore, we can put the green edge in and take this. There is a black edge that we can take out that is not cheaper. And so this creates, this is again a tree. The cost doesn't go up. So again, we get a minimum spanning tree, and this is S prime. Okay? Good so far? Good. Okay, so how much time do I have? I have 20 minutes to talk about, okay, that's possible. So why do you need to know two minimum spanning tree algorithms? So as I was saying, I mean, you can use Kruskal's, for example, Kruskal's is, you can use Kruskal's in a distributed system where everybody is sort of trying to do things in parallel. Prims you can use if you have only one road building machine. But there's a trick to Kruskal's that only comes out. Did anybody, do you think you could implement Kruskal's algorithm? So let's see the list. Who thinks they could implement Kruskal's algorithm? Hands up. Okay, maybe you can, but not with the data structures you've seen so far, unless you saw more fancy data structures than the people in the fall semester did in their version of 2110. Why? Because Kruskal's, remember in Kruskal's, I was going around saying, okay, so you've sorted the edges. You can sort things. You know how to sort things, okay? So you sort the edges, fine, you can do that. Now I'm saying, so you consider this next edge. Does it create a cycle? Well, how do you find out if it creates a cycle? So in Prim's algorithm, it's easy to tell if it creates a cycle, because whenever you add a vertex to your single tree, you sort of mark that vertex. And then if you want to know if an edge creates a cycle, you just look if its endpoints are both marked. Okay, so that's easy. But in Kruskal's algorithm, you have a lot of trees, and you want to know if, when you look at an edge, are its two endpoints in the same tree? That's not so easy. I mean, you could do like a breadth first traversal from one of the endpoints and see if you get to the other endpoint, but that takes like linear time in the size of the component that you've built so far that contains that endpoint. So it's not fast. Okay. So before I go any further, I should ask: did anybody who put their hand up? Somebody asked something. Okay, somebody said shit. So have you seen a data structure called union find? Good. Okay. So the union find data structure I think it's in the textbook. We're not going to do the full analysis because the full analysis is really hairy. But I'm going to talk about. So, okay, yeah, okay. I got the order slightly wrong. So you can see that, I'll get to the union find in a second. Prim's algorithm, how would you do Prim's algorithm? Well, you pick some vertex, and then you consider the edges incident to that vertex, you sort them, and then you take the cheapest one, okay? And then whenever you add a new vertex to your tree, you take the edges incident to that vertex, and you put them in a data structure. So you want to always have a list of the edges incident to your current tree. And whenever you connect a new vertex, you want to take the edges incident to that and put them in this list, and you want this list to always be sorted. We call that a what? You would do this with a priority. Actually, so I wrote, you can read this. This actually says queue. Priority queue. Yes, you would do that. For example, you do this with a heap. You do this with a min heap. So that whenever you connect a vertex, you take all the edges incident to that vertex, you put it in the min heap. And that way, at each step, you ask the min heap for the minimum cost edge, it gives it to you, and then you just check to see if it connects two nodes that are two vertices that are already in your tree. So min heap, you've seen, I hope. Otherwise, otherwise go off and read about min heaps. So that's with a priority queue. So you can actually implement Prim's algorithm. Kruskal's algorithm, now we're going to do union find in the remaining 16 minutes of the class. Good. So now we don't need this stuff because we've seen the proofs of correctness. So we want a data structure that starts off, a lot of elements are in separate trees. And now if we connect two of these, we want to be able to ask, if we ask for, so an edge is a pair of elements, and we want to be able to say, are A and B or A and H or whatever, are these in the same tree? So the idea is, now we're gonna do this with more trees, but these trees are not like graph things, these trees are data structures. So what we're gonna do, just to save time, because I have 15 minutes, Okay, so let's suppose we have A, B, C, D, E, F, G, H, I. Okay, so, oh, poof. I erased the list of stuff we did. Oh well. So let's suppose it doesn't, okay. In a perfect world, in a perfect class, I would do the same, I would use the same example. Maybe I can, because that's out of the textbook. In a perfect world, I would also be sufficiently organized to so we connect G and H, okay? So what happens is we take the node labeled G and make it the child of H, okay? So G now points to H. So this is now a data structure. This is not our graph, okay? So everybody is going to have a pointer to its parent, or, I mean, originally everybody points to itself. Okay, I'm too lazy to draw these self loops. So everybody has a pointer to its parent or its representative, its parent, and then they're not pointing to anybody. So G points to H, and H points to itself. So now, if I ask you, so every tree has sort of a representative. Okay. So this is the union find data structure. So what the two operations it supports are union to two trees, to groups, to sets. So this is it stores disjoint sets. Each set has a representative, and the operations are union to sets, or given an element of a set, find its representative. So I can say union GH, and find G will return H, and find H will return H. Okay? Are people following? So now, what is the next step? Union, they do CI. Okay. So now C is going to point to I points to itself. So, and then union FG. Okay. So now, when I union FG, this is actually, I'm unioning this set with this set. I always do this by having one, I maintain that these are trees. Okay, so I always set the root of one of the trees to point to the root of the other tree. But the rule is I always make the root of the smaller tree point to the root of the bigger tree. So when I say, when I want to check if F is in the same tree as G, I say find F, it returns F. Find G, it returns H. And F and H are not the same representative, so I know those are two different sets. So then I say, okay, union F and H. So the rule is always make the smaller tree point to the bigger tree. Okay. So now they union A, B in the book. So they're the same size. So I say find A, it returns A. Find B, it returns B. They're not the same. So they're different sets. So A points to B. And then there is FC. So find F returns H, find C returns I. And now so they're different, so I can put that edge which joins those two trees. So, and I always want to make the smaller tree point to the bigger tree. So this becomes C points to I, and I points to H. Okay. Can we do here B points to A? Yes. In that case, because the tree is the same size, it doesn't matter. Okay. FC, and then, okay. Uh-oh. Okay, yes, here, then the next node, the next edge they consider is GI. Find G returns H, find I returns H. It's the same set, it's the same tree, so that edge is between two nodes in the same subtree, in the same tree, in our forest, in the forest Kruskal algorithm that is built so far. So it creates a cycle, so we don't add it. Okay. So find G. Okay, I'm not going to find G returns H, find I returns H. So don't do anything. And then, okay. So, yeah, just to finish off, because I have 8 minutes. Where was I? Oh, yes, okay. CD. So now CD, find C returns H, find D returns D. So now I can say, okay, D, but D doesn't point to C, D points to the representative. Okay. CD, where is CD? CD, and then finally I see HI. HI, find H, returns H, find I, returns H. We don't do anything. So you keep going like this until, okay, well, we're going to have a couple more steps left. So HA, find A returns B, find H returns H. So we're going to add. Now B is going to point to B is going to point to H, and then finally we see, okay, we consider the edge BC. This is in the textbook. Okay, we consider the edge BC. B returns H, C returns H. We don't do it because it would create a cycle. They're in the same tree. And then we see edge DE. E returns E, D returns H. So they're not. Well, actually, okay, so now E is going to point to H. And then, finally, just to finish off, FE, F returns H, E returns H, same tree, that creates a cycle, so we don't add it. BH, B returns H, blah, blah, blah. Okay, you can fill this in. So, in 6 minutes, I have to explain, so you could implement union find. Now, there are 2 tricks with union find that actually make it go faster. Okay, it's not that hard to implement, but there are 2 things which make it work, which are sort of, one of which is not too hard, and we're going to see now, and the other which makes it super magic, and we're not going to figure out why that works. The first is this merging rule. I'm always going to merge the smaller tree into the bigger tree. So so if I have already taken, suppose I have already done find X, find Y, say find A equals X, find Y equals, find B equals Y. Okay, if I have already found the roots of 2 trees, it is really easy for me to make one point to the other. And if they store their sizes, then I can make the smaller one point to the bigger one. Right? Because when I make the smaller one point to the bigger one, then I just set x's. So we have, so here we have a, here we have x, here we have y, and somewhere in this tree you have b. And now you say find a x, and x says this tree has 12, and y knows that this tree has 21. And then you say, okay, I make x's pointer is now pointing at itself. Instead of pointing to itself, I make it point to y. And then the size of x's tree stays the same, but the size of y's tree goes up by 12, so it's now 33. Okay, that's constant time. Some people don't really like pointers. I don't know how to explain this in terms of objects. You probably can, but I like pointers. If you don't like pointers, they're super cool. You should learn about them. So union, once you've done the two finds, the union is constant time. So union we like. Find, if we just do the rule that I have 4 minutes, if we just do the rule that we merge the smaller tree into the larger tree, then find can't be too slow. Okay? And the reason is, if you have something here, okay? Well, whenever you would have done a union with this, so it can have a parent, and its parent can have a subject. Possibly this is empty, right? But then this can have a parent. So now you think, when you did the union here, when you made this one point to this one's tree was bigger than this, or not smaller, right? So now this can also have a parent. This can also have a parent. What can you say about the size of this whole subtree when you did this union? Notice that you have to do the unions down here first, because otherwise, if you'd done this union before you did this union, then this guy would point root. So these unions happen first. So what can you say about this blue subtree? Sorry, red subtree. What can you say about the size of that versus the size of this? Well, this has to be at least as large because you made this one the child of this one. If this were smaller, you would have made them the child of this one. So every time you go up from a node to its parent, you're at least doubling the size of the subtree. Okay? So and the whole tree is on n nodes. Is at most n nodes. If you start off for cross-consonants and vertices. So what is the maximum depth you can start at? Well, if you're doubling every time you go up one level, and you go from at least 1, and you end up at the root with at most n, it can't be more than depth log n. So find, if we just do this simple trick of merging when having the smaller tree point to the larger tree, you're guaranteed that union after finding the representatives takes constant time, and find takes logarithmic time. So if you do the analysis, this is going to take n log n time, which is like sorting. Okay? And the priority queue also, you can a min heap. How long does it take to do Prim's algorithm with min heap? Well, it takes n log n because the extract min and the insert both take logarithmic time. So actually it's m log n. Okay. So that uses up all of the time in the class, but I'm just going to go into the 5 last minutes so people can leave. You don't need to find out about this rule, which is called path compression. So the 2 rules that make union find magic are the merge makes the smaller tree point to the larger tree, and path compression is I do if I have some tree and I do, now maybe this one has a subtree, so I have some node and I say, okay, find A. And A goes up to its parent and its parent has some subtree. So A points to Q and Q points to M and M points to D, and then D finally points to X. Well, when I do that find, it's going to take logarithmic, most logarithmic time, O log n. But then, oh, okay, I'm a little bit over time. Then what I'm going to do is I'm not going to leave the tree like this. I'm going to flatten it. So now I'm going to go up, find the representative, and then go back and have D with its subtree. But then also now M, I'm going to reset it. M is going to point straight to X. And Q is going to point straight to X. And A is going to point straight to X. Okay? So now I flatten things down. So now the next time somebody asks me for the representative to A, I don't have to go to Q to M to D and to X. I just go straight to X. Unless somebody has union X with something else, in which case I go to X, and then maybe I go to the parent. So, and this makes union find super fast. It's not constant time, okay? But it takes something called O. This is alpha, and it's the inverse Ackermann function. And you can think of it as being constant. It's the slowest growing primitive recursive function. It's really, for any number you can possibly imagine, it's like at most 5 or maybe 6. Okay? So why do we care? Because that means if somebody gives you the edges sorted by weight, then you can implement Kruskal's algorithm using n, inverse Ackermann n. So almost linear time. Whereas with prims, you have to do a priority queue. Okay. So these are, for different circumstances, you want to use different algorithms. And I think this is easier to implement than a priority queue. It's just that nobody, no, that's not true. I taught the analysis of this when I was a TA in Toronto, but that was from my supervisor who was like, okay, sorry, thank you, Sarah.
Hi, Travis. I'll talk to you later.
Ciao, thanks.
Ciao.
Okay, so so that's, now you've seen that's a data structure. This is an algorithms course. You don't actually have to know. It's just, yeah, learn the union find data structure. It's really neat. It's in the course material from the fall semester. Okay. The session has left. Sarah has gone. Probably lots of other people are going too. I'm down to 14 people. Okay, I'm going to stop recording now. Bye, everyone. Have fun with the homework. Thank you to, well, maybe the thank yous are to Sarah. Okay, I'll stop recording and disappear. See you next week. Stop recording.